Okay, let's dive right into this. We are making a highly detailed video explainer today to completely demystify the incredibly hyped world of quantum computing. We're going to take you all the way from the underlying physics, the real nuts and bolts, straight through to the actual hardware roadmaps being built by the biggest tech companies in the world right now. We've got a ton of ground to cover today. First, bits versus qubits. Then, the mechanics of quantum. Third, the hardware race. Fourth, the problem of noise. And finally, the roadmap to reality. Let's get to it. So part one, bits versus qubits and the fundamental shift this represents. Now, you might be wondering, what is a computer anyway? Well, at its core, whether it's the smartphone in your pocket or a massive server sitting in some data center, a classical computer is just a device that encodes and processes info using binary digits, bits. Every single operation boils down to deterministic logic manipulating these ones and zeros. Basically, it's just a massive, complex network of tiny switches that are either perfectly on or perfectly off. And this brilliantly illustrates the core difference between the old and the new. Classical bits process information sequentially. It's exactly like trying one key after another until you finally find the one that opens a lock. Tedious, right? But quantum systems use qubits. Because qubits can exist in a superposition of 0 and 1, a quantum computer explores massive permutations simultaneously. It's literally like testing all the keys at exactly the same time, and letting the lock itself guide you toward the right fit. It's a real game changer. Looking at this shift from sequential binary processing to simultaneous superposition, this is exactly what gives quantum computing its exponential power. It's really important to understand that it's not just a faster classical computer. Actually, scratch that. It's an entirely different way of solving high-dimensional problems, things like optimization and complex molecular modeling, where classical computers just get totally bogged down by way too many variables. Moving right along to section 2. The mechanics of quantum and how qubits actually work. The first defining property here is superposition. This is the absolute engine of quantum parallelism. It's what allows the system to hold multiple possibilities at exactly the same time. But, well, here's the catch. A qubit only remains in this blended 0 and 1 state until you look at it. The moment you measure or observe a qubit, bam, that superposition collapses, and it's forced to choose a definite classical state of either 0 or 1. The second key property is entanglement, and this is wild. Entanglement is what links these superpositioned qubits together. When they become entangled, they basically form a unified fabric. If you change the state of one qubit, it instantly affects its entangled partners, literally no matter how far apart they are. In a quantum circuit, this lets the computer process information collectively. It amplifies the correct outcomes of an algorithm and basically uses destructive interference to cancel out all the wrong ones. So, the crucial takeaway here is that a quantum algorithm follows these 4 exact steps to leverage those physics. First up, initialization. You set the qubits to a known state, usually 0. Second, gate operations. You apply quantum gates to manipulate their states into that superposition we talked about. Third, you use interference and entanglement to amplify the right answer. And finally, step 4, measurement. You collapse all that crazy quantum probability into a classical string of ones and zeros that we can actually read and use. All right, section 3, the hardware race, and building the quantum engine. Taking these physics out of a textbook and into the real world requires literally some of the most extreme engineering on Earth. To keep these fragile quantum states stable, a lot of the hardware being built today has to be housed in massive, multi-million-dollar dilution refrigerators. For instance, superconducting circuits from IBM and Google, they have to be cooled down to around 15 millikelvin. To put that into perspective, that is literally colder than the ambient temperature of deep space. Incredible, right? Now, looking at the competitive landscape, there really isn't a single right way to build a qubit yet. You've got superconducting circuits favored by IBM and Google, super fast, but they need that extreme cooling we just mentioned, and they have pretty high error rates. Then there are trapped ion systems from companies like IonQ. They use atoms suspended in vacuums. Highly stable, great coherence, but a bit slower and harder to scale. And then you have photonic systems from companies like Xanadu using particles of light. Amazingly, these operate at room temp, but reliably entangling those photons? Yeah, incredibly difficult. Every single tech giant is trading off speed, temperature, and error rates trying to build the ultimate processor. Which brings us to section 4, the problem of noise, aka the ultimate villain of quantum computing. No matter which hardware modality you're looking at, they all face the exact same massive roadblock. And this number is just staggering.
Today's absolute best physical quantum processors have a gate error rate of about 0.1%. That means they make a mistake roughly once in every 1,000 operations. Compare that to the phone or laptop you're watching this video on right now. That creates an error maybe once in every quintillion operations. That is an absolutely enormous gap in reliability.
The culprit behind this gap is a phenomenon called decoherence. Because qubits exist in that incredibly delicate probabilistic state of superposition, they are just unbelievably fragile. Literally the slightest environmental noise. We're talking a microscopic temperature fluctuation, a tiny vibration, or even background cosmic rays, causes decoherence. It prematurely collapses the qubit state and completely destroys the complex algorithm the computer is trying to run. So, to actually achieve practical real-world use, we have to implement quantum error correction, or QEC. Think of it like bailing water out of a leaky boat. If the hole is too big, the water rushes in way faster than you can bail. But if you can suppress those errors enough, your bailing outpaces the leak and the boat stays afloat. In the quantum world, this means redundantly encoding one perfectly stable logical qubit across a whole bunch of noisy physical qubits to detect and fix those errors on the fly before the calculation is ruined. Finally, Section 5, the roadmap to reality and the path to fault tolerance. A massive hurdle here has always been that older error correction methods required thousands, sometimes millions of physical qubits just to create a single reliable logical qubit. But recently, IBM introduced a highly efficient mathematical code called QLDPC, specifically the bivariant bicycle code, which is a pretty fun name. This is a massive breakthrough because it reduces the physical qubit overhead by up to 90%. It essentially proves we aren't going to need to build impossibly huge machines just to run reliable quantum programs. And this breakthrough maps directly onto a really concrete timeline. IBM's roadmap clearly lays out how they're going to modularly scale their chips year by year to leverage this new code. In 2025, the Loon chip brings in advanced couplers. In 26 and 27, Kookaburra and Cockatoo bring in modularity, literally linking separate chips together so they don't have to manufacture one gigantic, impossible chip. This whole shebang culminates in 2029 with the Starling system, which is slated to be the world's first large-scale fault-tolerant quantum computer, rocking 200 logical qubits. And here is why this absolutely matters to you and me. By hitting these milestones, systems like Starling and eventually the 2,000-qubit Blue Jay system in the 2030s will finally cross that threshold from experimental lab equipment to world-changing utilities. We're talking about running circuits with hundreds of millions of gates. That unlocks the ability to solve massive real-world challenges in drug discovery, materials science, and cryptography that our current classical computers couldn't even dream of touching. So it really leaves you wondering, once we finally overcome the noise and reach full fault tolerance, what currently impossible problems are we going to solve first? When a machine can test every single key simultaneously, there is literally no limit to the doors humanity can open. Thank you so much for joining me on this detailed explainer today. Keep learning, keep questioning, and I'll see you next time.